Welcome everybody to the final webinar of the NextGen Microfluidics project. Today we have our third demo case in the project, which is also in our last webinar, on smartphone-enabled home diagnostics for potassium in blood, with two presenters from the NGM project. The first is going to be Martin Heinczek from Erbe Technologies Austria, based in Graz, and the second will be Caroline Kolleger from Infineon. Before we start with their presentations, I'll give you just a short overview so you know where we're at. I'm Caitlin Ahern from BNN, responsible for communication and dissemination in the project. And we are coming to the end of our project now and want to share some of the outcomes with the greater public. So what is NextGen Microfluidics? This is an EU-funded project given 17 million euros to address problems and fragmentation in the microfluidic development. So this project brings together 21 service providers along the value chain of microfluidic development, from design and simulation, through materials, through sensors, research, process development, and so on. In addition to offering these services, the project has founded an association called Microfluidics Innovation Hub, which is now our 22nd partner in the project, which is serving as a single entry point to all of these services offered by the MIH and NGM service providers or partners. Within the project, we had 5 demonstration cases to verify the services and how we can work together, having multiple service providers along one project with a single entry point. These demo cases we've been talking about in our webinars. You'll hear one of them today. If you're interested in hearing more, we have the recordings of our previous webinars on the NextGen Microfluidics website. And we'll tell you at the end about an event we'll be having next week. In addition, we had an open call where we funded 18 different projects, which were managed by the Microfluidics Innovation Hub. And we also have some success stories of these on our website, on the MIH website, and developed 22 application areas for the services. So that's just a brief overview. If you're interested, please check out our website after the webinar. But now I'll hand it over to Martin Heinczek from Erbe Technologies.
Thank you, Caitlin.
Okay, now you should be able to share.
Where is it?
Okay, now you should have it.
Yeah. All right, can you see the slides?
Yep, perfect.
Perfect. Okay. Yeah, welcome everybody. I will talk today about smartphone-enabled home diagnostics for blood potassium. I'm from Erbe Technologies Austria, and I think Erbe isn't really known in Europe. Therefore, I have some introduction slides of our company. So Erbe Technologies Austria is part of the Erbe Mannheim Group. That's an international company, located in India. And this Indian company decided to reach out to European research and development capacities, and therefore they bought 5 R&D sites in Europe, France, UK, Czech Republic, and in Austria. And in Austria, it's Erbe Technology Austria. Erbe Mannheim is still a private-owned company, and as the vision says, they are rooted in emerging markets, and the company is dedicated to serve emerging markets. That means that Erbe Mannheim focuses on making innovative diagnostic technologies accessible to people in low resource settings. So we are talking about Asia and South America, which are our main markets for our products. The group itself has a comprehensive product line for small and medium-sized labs, covering the whole spectrum of diagnostic instruments that are used in hospital labs. And Airbus Technologies Austria has a focus on critical care. So we are developing instruments for critical care and point of care blood measurements. And our flagship product is the EZ90. That's a small benchtop analyzer, which is maintenance free and measures ions like sodium, potassium, chloride, and calcium directly from the blood sample, but also in plasma serum and urine. Okay, this is where we come from. And now I move on to the next-gen microfluidics project, where we lead a demo case. And yeah, I would like to start by talking about our motivation to develop this smartphone-enabled point-of-care device. I think all of you know diabetes patients who need to monitor their blood glucose levels on a regular basis. And there are other diseases like chronic kidney disease or chronic heart failure. Those are diseases where not glucose is the interesting parameter, but it's blood potassium. And for this patient group, we want to develop a point-of-care device or a home care device that enables the patients to measure their blood potassium at home. Those two patient groups are a quite high number of patients. So we did the internet research and found out that about 10 to 15% of all adults over 65 years suffer from kidney disease and or chronic heart failure. And these are about 190 million patients in the developed countries, so in Europe and the United States. So that's really a huge market for such a product. And patients would benefit a lot from such a home care device because they do not need to see a doctor in the doctor's office to get their blood potassium monitored. And when they are monitored in shorter intervals, then also emergency hospitalizations could be avoided. So now I will talk a little bit about the technology behind our point of care solution. So we are integrating microfluidic structures with electrochemical sensors in an integrated sensor card that allows to measure the blood potassium value from just pricking the finger and measuring in this small drop of blood, and use your private smartphone for the measurements. So the smartphone controls the measurement and also displays then the test result. So we have a microfluidic structured foil that carries the microfluidic structures, and this microfluidic foil is then combined with the sensor foil that carries the electrodes for the detection with a screen printed adhesive layer. We also have integrated a plasma separation membrane that excludes the red blood cells from the drop of blood and let only plasma enter the measuring channel of the sensor card. And we have a fixation for the plasma separation membrane that keeps the plasma separation membrane in the sample inlet. And we bring these things together to create this integrated sensor card. So the microfluidic foil in the detail, we have two inlets in the microfluidics. There is the blood inlet. As I already said, this blood inlet also carries the plasma separation membrane to create plasma from the blood sample. And the blood inlet has also a special finger-like structure that allows to collect the plasma from the plasma separation membrane and guide it into the measuring channel. The second inlet is the inlet for the calibration solution, because we need a one-point calibration of the electrodes for the potassium measurements to then calculate the correct blood potassium values based on the electrode readings. The electrodes of the sensor are sitting in the sensor channel. Here we do not only have the reference in the working electrode for the potassium sensor, but also two electrodes for a conductivity measurement. This allows us to check whether the measuring channel is completely filled with the sample, and we can start measuring. And at the end of the microfluidic structure, we have this big structure that works as a capillary pump, but also as a waste reservoir, because we need to contain the sample volume and also the volume of the calibration fluid on the sensor card. The microfluidics were designed and optimized using computational simulations that helped us to design the whole microfluidic design from the inlet to the waste reservoir. Special focus or a special challenge was the design of the inlet, where we created these small micro channels. So we call it the finger-like structures, which increases the speed of collecting the plasma from the plasma separation membrane and to guide the plasma into the measuring channel. The potassium sensor itself is, to say, a classical ion selective electrode, but it's miniaturized and it's screen printed, so it can be produced at very low costs. The working electrode consists of a carbon working electrode that's covered with a PVC membrane carrying valinomycin as a ionophore. And with this sensor, we are able to accurately detect the blood potassium concentrations by using this one-point calibration of the sensor baseline. And we have tested the sensors, so we have a shelf life of over 6 months. There's also no temperature influence on the measurements at ambient temperatures. And also the slope of the sensors are really stable. And this allows us to detect the upper and the lower limit of the physiological range of the blood potassium values, and to give the patient the warning when blood potassium values are too high or too low, and to motivate them to see a doctor or change the medication if they are taking diuretic medications that interfere with the electrolyte balance in their body. Here I have some pictures of the microfluidic chip again. The chip itself, it's produced with a roll-to-roll process that's called extrusion coating, where the microfluidic structure is embossed in the liquid polymer. And this technique has a big advantage that you can produce different channel heights in the same production process. So that's quite unique for producing microfluidic structures. And the pictures also show that these really small finger-like structures are formed very well with this technique. Yeah. Then one of the biggest tasks in our demo case was to bring the different parts together to integrate it to this sensor test card. So on the one hand, we have the sensor foil with the electrochemical sensors. We have the microfluidic foil with the microfluidic structures. So first, we need to bring them together. So we do this with a screen printed adhesive layer and bonding these two foils together. And the next step is the microchip mounting. That's a task of heterogeneous integration of electronics on this soft polymer-based sensor foils. So the chip is mounted by using screen printing inks that are electrically conductive to produce the electric contacts from the sensor foil to the microchip. And we also need some mechanical stabilization of the chip that's done with an additional adhesive layer at the bottom of the chip to keep it safely on the sensor foil. For the system integration, we also needed to develop the fabrication process for the screen printed NFC antenna, because the NFC antenna is necessary for the communication of the microchip with the smartphone, and so that the smartphone can initialize the chip once the smartphone is in close proximity with the sensor card. And so when this is done, then Infineon has developed the app for the smartphone, and to enable the communication of the smartphone with the sensor card via the NFC field. The app guides the user through the whole test process, so each step is animated and the user is told what is the next step for the measurement. And I also have to emphasize that over the the NFC field. The chip also allows the energy harvesting, so there is no battery necessary on the test card, which is important as the test card is a single-use product. So we wanted to avoid having a battery there. And when the measurement is done, the result is displayed on the smartphone, and there are also possibilities to track the results in a diary and to have your history of your potassium values already handy on your smartphone. So this is the overview of our demo case. I'm open for question when there are already some questions. If not, I would hand over to Carolyn.
Yeah, everybody who has a question, you're welcome to write them in the question section or in the chat, or just raise your hand. And otherwise, we will come for questions at the very end. Thank you, Martin Heinczek from Irva Technologies Austria. And now we'll switch over to Carolyn Kollegger from Infineon Technologies.
So thank you, Caitlin, for the introduction, and also thanks to you, Martin. A warm welcome from my side to the audience. It's a pleasure to provide a quick, share my webcam, yes. Now you can see me.
Anyway.
It's a pleasure to provide a quick look at the ASIC XS chip platform. My name is Caroline Kollegger, and I'm an application engineer at Infineon Technologies Austria. So the Infineon chip is built for precision measurement and is highly versatile, supporting a wide range of applications. Its standout features include an integrated NFC interface. This allows for secure wireless data exchange with NFC-enabled devices like smartphones or readers within a range of a few centimeters. It also supports energy harvesting from an NFC reader's electromagnetic field, making it possible for the chip to operate without its own power supply, which is ideal for low power or passive systems. It's equipped with a Cortex M0 microcontroller and 128 kilobyte of flash memory, ensuring smooth and efficient system integration. The built-in power management unit carefully regulates and distributes power across the chip's components and even to connected external devices when needed. The 6-fold sensor interface can connect up to 6 electrochemical sensors, enabling it to monitor multiple reactions or analytes at the same time. This boosts efficiency and expands the range of use cases. On the next slide, I'll dive deeper into the measurement portfolio this chip supports. Can you go back one slide, please, Martin? Sorry. With a real-time temperature sensor, the chip can manage its internal temperature to prevent overheating. And this feature also supports temperature-dependent sensing, which is really essential for specific applications. The ASIC XS platform stands out significantly, reducing the bill of materials without compromising functionality. It has been strictly tested, achieving technology readiness level 8, which highlights its reliability and readiness for real-world deployment. So please skip to the next slide. Yes. Our chip can measure both current and voltage, making it a great fit for a wide variety of sensor applications. It supports advanced measurement techniques like square wave voltammetry, dynamic pulses, chronoamperometry, ensuring flexibility for different use cases. Thanks to its 6-fold sensor interface with potentiostatic functionality, the chip is well suited for detecting biomarkers such as lactate, glucose, CRP, potassium, pH, and more. This makes it a powerful tool for applications requiring accuracy and reliability in monitoring complex biological or chemical signals. As part of the NextGen project, the chip was designed to ensure no current flows during specific operations, particularly in OCP mode, open circuit potentiometry mode. This high impedance mode prevents interference in environments prone to disturbances such as those affected by LED activation, radio signals, or external noise. By blocking current flow in OCP mode, the chip maintains precise voltage regarding voltage readings, even in challenging conditions. So in summary, the ASIC XS microchip showcases Infineon's dedication to creating innovative solutions that tackle complex measurement challenges with precision. So it's a reliable and forward-thinking platform that reflects the commitment to building a safer, greener, and more efficient future. So thanks, that's all from my side.
Great, thank you so much to Caroline Kolliger from Infineon Technologies here in Austria. We'd love to open it up to questions from the audience. So again, you can raise your hand, write in the chat, and we'll try to unmute you to ask your question. While we're waiting, I would have a question just to get us started. So Caroline, while you're still with your mic on, are there commercially available products that are similar to the, do you say ASIC platform? And if
Yes.
so, how does yours differentiate?
Yeah, there's the well-known PalmSense device, which is a laboratory equipment. And the difference between the ASIC XS and the PalmSense device is simple. The ASIC XS is one of a kind, IP protected innovation created to meet the needs of portable diagnostics. So unlike this traditional lab equipment, which tends to be bulky, expensive, and fixed in one place, our chip brings everything together in one compact chip. So it handles signal conditioning, sensor interfacing, and wireless connectivity all in one solution. And this makes it possible for point-of-care devices to deliver lab quality performance while staying portable and easy to use.
Okay, and one aspect that you mentioned was the sustainability. So this is very important for us at BNN. Can you tell us a little bit more about that?
Yeah, our chip reflects Infineon's mission to make life easier, safer, and as I mentioned before, greener by focusing on sustainability through energy efficiency, material savings, and accessibility. Its cost-effective design make advanced diagnostics more, let me say, affordable, which opens the door to improve healthcare, especially in developing countries.
Great, thanks a lot. Going back to Martin, I have to say that before working with you in this project, chronic kidney failure was not so much on my radar. I didn't realize how prevalent it was until you had shared these statistics. Was there a certain motivation that you had in choosing this application that you could tell us more about?
Yeah, so in my former job, I developed glucose sensors for diabetes patients, and I also did a long time cooperation with the medical university in Graz. And in our discussions, it came up that it's not everything in the sensor world is about diabetes and glucose sensing. So there are also other applications and really huge patient groups that could benefit from a home test device. And yeah, in this discussion, we found out that patients with chronic heart failure and chronic kidney disease are a huge patient group that would benefit a lot from a home monitoring device for blood potassium. And we thought that potassium is not that extravagant parameter, so it should be possible to make such a technology available for this patient group. And so we started with little steps to use our glucose sensor technology for the diabetes patients for these new patient groups, and started developing this potassium home monitoring system.
We hope that it gets into the hands of a lot of patients in the future. Was there any aspect of this project that was the most challenging?
Yeah, so there are two things that were really challenging. One thing is that, so I'm again comparing with glucose monitoring. So glucose is quite easy to measure because when you have your finger prick, you can measure glucose because the sample isn't really altered. When you do finger pricking and you push your finger to get the blood of drop out of the finger, then hemolysis could occur. That means that red blood cells get destroyed. And this can change the potassium concentration of your sample, and this makes the measurement of potassium more tricky than glucose. And during this development, especially this smartphone-enabled potassium measurement, was also challenging us to develop new things we didn't know, because we are sensor developers, and now we had to develop in production process for an NFC antenna, and mounting this electronic chip on the sensor card. So these system integration steps were also challenging for us, but I think we did quite a good job.
Great, thanks for sharing.
We from Infineon's side also faced some challenges because the chip's flexible design had to be tailored to meet the specific requirements of the sensor manufacturer. So already during the design process, we developed the hardware to be competitive, capable, and firmware enabled. By doing so, we adapted mostly firmware and software to ensure optimal compatibility and performance. And for the potassium sensor, the chip uses this open circuit potentiometry, this method where no current flows through the sensor to accurate measure its voltage output. And one of the key engineering challenges was that the was designing the ASIC XS to maintain this zero current condition while ensuring high input impedance and keeping power consumption low.
Okay, thank you. What about from the audience? Are there any other questions at the moment? You can raise your hand or and we'll unmute you to ask. Yes. Stefan Kessler. Let me see if I can unmute you. Okay, see if you can unmute yourself.
Okay, does it work?
Yes, no, it works, yeah.
Okay, now it works. Okay. Well, hi Martin, hi Caroline. Thanks for a nice presentation. Just one quick question from my side. I think we perfectly do agree that potassium home monitoring is a great thing and that should be become available. And you, Martin, you already mentioned, let's say, about the hemolysis problem, but I just wanted to ask, are there any other parameters that you have in mind that could be done with the same or similar technology? On the one hand, let's say with the NFC technology from Infineon, and on the other hand, more in general, that let's say, is there any kind of plan of include other analytes or parameters that could be detected instead of potassium, or let's say like the hemolysis thing that you mentioned along with potassium that you have in mind for this type of application?
Yeah, it would definitely make sense to integrate more sensor in such a sensor card. They should be tailored to the specific needs of the patient groups. So thinking about patients taking diuretic medications where also sodium could be an interesting parameter. To add sodium to the potassium sensor and also to integrate the hemolysis detection. That would really be a great benefit when you can tell the user that the sample isn't valid because the finger was pressed too hard during the sampling process.
Okay, I'm not sure if he can unmute to respond.
Yeah, thanks a lot. And let's say, especially maybe to Caroline, or let's say, are there any further, I would say, activities ongoing to include the NFC enabled electrochemical interface that you just presented to other, let's say, applications apart from the kind of, let's say, CKD patient home monitoring thing?
You, did I understand you right that you are asking if we have other projects running in parallel which are dealing with the biomarkers I mentioned before?
Yeah, somehow.
Yes, of course. Each biomarker I mentioned before is running somehow in an application we are dealing at the moment.
And they are all mostly, let's say, related to type of home monitoring, or at least near patient application that would justify a very low, very high volume of consumables that could be equipped with the NFC part. Yeah. Okay.
Yes, you're right.
Okay, thanks.
All right, thank you. If there are no further questions, then we would just love to tell you about an upcoming event and where you can find us. So next week, we are having our final dissemination event as a satellite conference of the Health Tech Hub Styria here in Graz, Austria. It's called the Next Generation of Microfluidics, linking expertise across Europe, coordinated in Austria. So here we'll be hearing from our other demo cases and this one as well. So Martin will be back on stage, but also hearing from some of our open call success stories from some external speakers that we've invited from the Austrian microfluidics landscape. And we will have hands-on demonstrations of the technologies and a kind of technology showcase and networking event. So it'll be quite full of interesting opportunities, and we'd love anybody who's nearby to stop by. Our section is on the afternoon of March 26th, The whole conference is from the 25th to 26th of March. You can find more info on our website. I put the links in the chat. And if you want to take advantage of the services offered by the partners of NextGen, after our project ends, the Microfluidics Innovation Hub will remain, and they will be offering these services along the value chain. So please check out microfluidicshub.eu and the service portfolio there. So we'd like to thank everybody for coming, and I want to say thank you to our speakers, Martin Heinczak and Caroline Kolliger, and we hope you'll stay in touch. Thanks a lot, everybody.